Okay, it looks like we're just about ready to get started. So welcome to everyone who is joining us today for our Reactor session. Do feel free to check in for today's event using the details on the screen. So checking in will give you information to resources and information about upcoming series at the Reactor that are around similar topics to today's session. So the details are on the screen and you're more than welcome to check in. Today's session is part of the natural language processing series that's been running over the last few weeks. And today's particular session is state-of-the-art language models. So this session will run over the next 60 minutes and it is being recorded. Please feel free to ask any questions that you have throughout. So there's a Q&A window that will be moderated by myself and Robin. So any questions that you do have, feel free to pop them in there and we will make sure you have the answers by the end of the session. To quickly run through our code of conduct, this is just a reminder to everyone today to be aware of one another, friendly and welcoming throughout as we run through today's session, and just understanding of any differences of opinions that we might see throughout the chat or any Q&A that we have too. So today's speaker is Lida. Lida works as a cloud solution architect at Microsoft, and Lida has already delivered a couple of sessions with us throughout this series, so delighted to be welcoming her back again today, and we'll hear a bit more from Lida in just the next few minutes. Just to recap what we have already covered in this series. So this has been an 8-part series and today marks the final episode within this series. So as you can see on the screen, the first 4 weeks throughout this series, we ran various different topics, all of which are available to watch on demand. I will drop the link into the Q&A window of where you can find those. And then the last 4 weeks, you can see as well the different topics that we ran, finishing off the series today with state-of-the-art language models. So without further ado, Lida, I will hand over to you to get us started today.
Yes, thank you, Emma. Hello, everyone. Thank you for attending this call today. As Emma said, this is the last series of NLP series in Reactor, and I have the privilege to finish the series, the great series that we had through our great colleagues. And apologies, I think I'm sharing a wrong window with you. Just to give the overview of the topic today, is going to be quite a technical one today because of the concept of the talk. So please feel free if you want to if you ask any questions, happy to answer you during the call, or if you find it very kind of difficult to follow up, please feel free to follow up with me. I think I'm still messing up with this presentation. Okay, that should be fine. Right. When it comes to language model, people are often asking about what is a language model and how it's been applying. So I put together a slides from different places just to give an overview of this quite a complex topic in NLP that has had getting a lot of attentions due to GPT-3, the largest language model that was released last year, around this time. And because of that, I guess a lot of attention. So the intention of the slides today is mainly walk you through language model development and until to the state of the art, the 3 GPT language that have been released in the last 3 years. So let's start by what is a language model. It's basically a task of prediction what words comes. And I also need to say that some of these slides are given from other lectures. For example, this one is from Stanford University. I find the information very useful, so I just get the slide from them. But you see the source on the slide. So when we say the task of predicting what words comes next is like, for example, thinking of a sentence the students open there, and in the human mind we kind of think of, for example, books, laptop, exam, minds, or other words that can be kind of the bags or something like that. So the aim of a language model is, given a sequence words, what is the probability distribution of the next words? That is basically the concept behind it. And so this kind of thinking of what is this kind of system that in a number of vocabulary words, what is the next probability of the next word? That is a kind of a known as language model in NLP. So what are the language model application? You use them basically every day in your mobile. When you are kind of typing and there is a kind of suggestion already or a spelling corrections, this is done through language models that are pre-built in the network that you're using in your mobile application. Also, the recommendation or suggestion words in search engines. All search engines today use language models, so that's been embedded through the search engines. Or even the correction, kind of a spelling in your email provider, that also suggested by language model. Or even more advanced in both Outlook and Gmail today, they kind of even suggest you kind of the grammar correction if you have making a grammar correction, or the sentence doesn't make grammatically sense in English or the other language that's been said, the system correct it or give you a suggestion to correct it. That is all done through language model. So the common use cases of language model are sentiment analysis, question answering, translation, text to speech, which is a sequence to sequence, and a speech recognition, auto-completion. And in industry, in parallel with the advanced work in research for language model, we have Google Home, Amazon Alexa, Apple Series, Microsoft Cortana, that they're all kind of a intelligence visual assistants that are embedded through language model, because they kind of have a pre-built embedded to understand your inquiry, and they kind of respond to that. So this is like kind of the number of application. So you can also think of language model that can assign a probability to a piece of text, as I said it before. So it's a kind of a probability system. I think the idea of it is probability, but then the implementation of this probability has been changed as we go, as the language models are developed. One of the earliest, the people who did NLP in like last 10 years, which I did study NLP in 2011 until 2015 when I finished my degree. So at that point, N-grams language model were kind of very hot topic, and what was like kind of looking into the N-grams of chunk of the words. And then based on that, they would do kind of making some prediction of what is the probability of these two languages can appear together. And of course, you could have unigrams, bigrams, trigrams, and sometimes even there are 4grams. But most common approaches was bigrams and trigrams. And it was the lot of classical NLP solution actually work well with n-grams, or even in terms of topic modeling, the kind of not the neural network approaches, but the classical way of topic modeling, also looking into these n-grams chunk collections. So it basically was really good in terms of collecting a statistical how frequent different n-grams appear together, and then they would give a weight to the entire context. Of course, this wasn't really a kind of a solution for this fast pace of AI application. That's the type that the next generation of kind of looking at the probability of words was word embedding, which is a type of language model that is a technique that kind of map words and phrases to the vectors of real numbers. So rather than looking into the words in the actual kind of their occurrence in the context, it's giving a vector a number to it, that is in the learner workers the words would have some synthetic and semantic relationships together. And often what happens in word embeddings, we see that the relationships of words are captured together, because what happened is in that kind of 3D visualizations that show all the kind of representation of words, the words that have similar meaning and semantics, they appear next together. For example, man to woman, king to queen, or walk to walking, swam to swim, and so on. So word embedding, the main one was 2013, started by Google, word to wake, and it followed by Glove from Stanford, and then fastest by Facebook. And there are a lot of improvement on word embedding, but the changes happen here, that rather than looking at the word itself, looking at the numbers. So having said that, still word embedding, although it was an improvement, but still the questions was, if we look into the input of sequence of words, we want to have the probability of the distribution of the next word. That's a foundation, like a fundamental definition of language model. How about if we look into a neural language model? So neural network are the implementation, are the start of the conversation of deep learning in machine learning. So, but neural network is basically trying to represent the input of whatever input you got, not necessarily words. It could be sequence of voices or images or pixel of an image. It goes through a number of hidden layers, and then there will be some calculation on that hidden layers and hidden relationships. And then there will be a kind of an answer to the kind of occurrence that we want to find. For example, is it a classification, or is it a kind of text to speech? What is the next words, guessing, and so on. For example, a window-based neural network for name entity recognition would look like something like that, it's kind of the sentence museum in Paris are amazing, are fed to the network, and through the number of hidden layers and weighting that they get, Paris come up as the final entity that would the network would recognize it as location. So this, having this idea in mind, we look into, there's a concept of fixed window neural language model, which known as kind of what it does is, after the concentration of converting the words or one hot encoding the vectors of the words, it calculates the word embedding of that words in that layer, in the first layer. And then there are, of course, number of hidden layer here. That's the kind of mathematical formula, but I'm not going to explain it in that detail. And there's, of course, there's a layer on any neural network model that that has a kind of a what to say regularizations of the outcome. So this is the softmax distribution output. That, for example, in that one, the outcome is showing the probability of books come very high, whereas the probability of the next one is probability of laptops, and the rest of the words are less probable. So this is how a fixed window neural network would look into it. And in that sense, it's only looking at the words at the time that they're entering. There is no kind of directions, like there's no back forward, it's all move forward network. And of course, there's no kind of complexity into how which words get most attention. By saying these points, I'd like to give you some hints for the next architecture that I will share in coming slide. So what are the improvements to compare a fixed neural network to Ngram's language model? Of course, we don't have the his parity problem, because with the problem within Ngrams that yeah, two like let's say a couple words can appear together a lot, but they may have different contexts. For example, good evening has a very different context to good morning. But then if they keep appearing together, the model, if not taking any context into the place, it will appear, it will think of any good evening has the same probability of good morning, which we know that this is a totally different setting. And the problem, another problem with a language model was they couldn't store all the observed Ngrams, but in this neural network we observed a kind of all the observation are stored. But what was the problem? The fixed window is too small. We're looking of sentences that need to be analyzed in a long setting, and this architect would not respond to that. And how big you can go as well. Like if you say, okay, I increase the size, but how big you could go. And then there wasn't any, as I said, there wasn't any probably agreement of how to put this input to the model. So then it's a need, there was a need of, we need a language neural architect that can process any length of input without any setting. That's the part that ARNN, known as Recurrent Neural Network, has appeared. So in that scenario with Recurrent Neural Network, there is a slight change, which is a big change actually, but in the architect, if you remember, in the previous slide, when we had the all the hidden, like a first layer and the hidden layer, the first layer wouldn't communicate. They were kind of, the communication level with the first layer was at the same level for all the words. But in recurrent neural network, there is a input of the first, like a previous hidden layer. Then also there is an input of the actual layer, the layer behind, like below, if you, it makes sense, more like if you think of it 3D. So because it is receiving all these two information at the same time, and then it making a decision for the next weight, and again the next weight gonna get affected by the actual input, and it keep happening. And there's also a, of course, there's a E factor here, and that kind of embedding has a significant changes into this weighting. And at the end, what been predicted, it giving it as a formula. I hope you can see it in that part, but that's a formula that been calculated for ARNN, and it is giving a very good probability again for books and laptop. So the main difference here, so let's look into that, apologies, let's look into the advantage of ARNN. So the good news is it can process any length of input because whatever, there is no fixed window. Any input, the layers just gonna increase. That's just that. And there's a computation step. That is a computation step that kind of needs to go many step backs, because if, let's say, if the outcome of this layer, this step changes, would affect the outcome of this stage. And then model size didn't increase at the same time. So even if you have longer input, you're still dealing with the same model. And in every step, there is a symmetry of how the inputs are processed. As I said, if I just change the input of these two words, we say very grammatically wrong, but we say the opened student there, the outcome would change of the language of the result, because it kind of taken this into effect that this is important, the order is important here. And but the disadvantage of RNN is we are quite slow, and of course it's quite difficult to go many step backs, especially RNN are not useful in question and answering, because if the question is in the kind of, let's say, in step 4 and your answer is step 4 and you're questioning in step 9, it doesn't have a memory to remember that. Although there have been improvement on ARNN, and there's another architecture, LSTM, but I'm not going to go to that one because it's still on a being language model. But this is like kind of what happened in the kind of with the language model. So this is around late 2017. That was the kind of this state of the art of language model. In late 2017, we got a novelty in NLP known as transformers. And there's a paper, attention is all you need, and I highly recommend you just to read it. It's a very interesting paper. And what the paper proposed an architect, it was a use of encoder and decoder. The original task in the paper was a sequence to sequence task, but transformer architecture since then has developed in all NLP application. And the principle of transformers, the innovation of it, to compare, for example, to ARNN, that instead that stack layers that is going to be having we needed to put a gate to remember it or do some steps back. Here is looking at the bi-directional attention, and that way, so every token would get attention from both sides. So this is the architect that has represented in the paper, and I acknowledge it's quite hard one to understand, and we are not going to spend so much time on that. But what I want to have a pay attention to this attention layer that has been added to the architect, and how the input kind of the positional encoding that it have happened, and how the input is feeding to the output attention. So that is the part that has the novelty. And of course it looks very complex, but the rest of the architect are kind of similar. You still have a softmax layer for the probability at the end. So good news is I've got a much more simpler one for you to have a look at it. So this is from this Medium blog. It's a very good one. I highly, it's the graphic, but I don't think in my code it works, but I suggest to have a look. But basically what happened in, let's say in a sequence to sequence, a translation task, when you have encoder, all of the encoder, and then you have the decoder, each encoder have a self-attention layer. And this is the feed-forward neural network, and then the decoder as well get a self-attention, and the outcome of encoder speak to self-attention of the decoder. That's why it gets quite a. It has been a kind of a revolution in NLP because it gets a lot of attention. It kind of overcome all the limitation of ARNN. So I want to make a pause here and ask if there is any questions, because I don't see in the window yet, because the next one is going to be, I think I can see the questions now.
So we don't have any questions yet, but if anyone wants to ask a question, please just enter into the live Q&A.
Yeah, okay, thank you, Robin. So I keep continue then. So I wanted just to make sure that I didn't overwhelm the audience by the questions. So moving forward, let's now move to the next concept of the actual topic of this. So I hope with this history you kind of get an idea that what has happened and why transformers are really important and make a big change in language model. So since transformers have been introduced, we got generative pre-trained transformers introduced by OpenAI. And there have been 3 language models since is the GPT-1, and the papers are also linked there. Please feel free to have a look. And there's a really good Medium blog that it's a very, very interesting way that they describe these 3 language models. So I highly recommend you to have a look at that. So look at the date here. Transformers was introduced in early 2017. In late time, the same year, we got GPT-1. And then around early 2019, you got GPT-2, and then you got GPT-3 in a year after. And that is showing that how the model has been improved and how each time the language model get evolved. And we're gonna look into the kind of each of the model details of each of these languages. GPT-1, the point about GPT-1 is often in machine learning people know asking about supervised learning or I'm sorry, I'm just reading. Yeah, it's been, the self-attention has been replaced by the transformer architect. Thank you very much for that. Unfortunately, I haven't seen this new published paper. I'm not sure, Alexander, but thank you for telling me. I will have a look at that. But I'm sure if they replace it with another attention layer, that probably they might probably be very interesting. I will definitely check that out. But the thing about transformers, the architect, every day you see a new development on it, and so I assume it's probably a good one that they kind of published it. So we will touch on how a transformer kind of performance can be checked. So to answer your question, if in the paper they compare this thing, so they probably have known about that. It's a good way to judge if there's been any improvement or not. So getting back to GPT-1, GPT-1 is very good for pre-training model because they kind of the concept was unsupervised language model has been kind of used in GPT-1 in the architect that GPT-1 has, and of course the concept of fine-tuning, meaning that you don't train the language anymore. You use the download the language model that has already been trained, something like BERT, and then you apply it on your specific text, and then because it kind of understand all the relationships in that context, in the context that has been trained, it been able to answer that particular query that you have. So I have a similar, I have a topic on fine tuning. The second topic that I presented on Kaggle competition. So have a look at that. And of course, GPT-1 was really good for task-specific transformation. As I said, for sequence to sequence, GPT-1 was very successful. What data set they used for GPT-1 was 7,000 unpublished books from books corpus. And because the good thing about it, because it's an unpublished books, it helped a lot with unseen data. And the other thing that about the model architecture and implementation design, GPT-1 have 12-layer decoder, and they also had a mask self-attention to train the language model. By mask self-attention, what they mean is some of the language, some of the inputs were kind of covered in a kind of, the model didn't know the meaning of the word. They kind of cover that, but then the model used the probability of the words before and after, because it's bi-directional. It's kind of, I guess, what was the word. That's kind of strong, and this masks self-attention using BERT as well. That's about GPT-1. So I want to pay attention on this decoder layer, because this number gonna increase for the next ones. With GPT-2, the main thing about GPT-2 is task conditioning, and there's a concept of zero learning shot or zero short task transfer, or if few shot learners. You have probably heard it if you listen to these conversations. Very in a layman words, if I explain what does it mean. When we say zero shot learning, meaning that we don't provide any context to the language model, we just ask an inquiry, and we don't give any hint. Basically, we just say, give me the record, give me, like, if you say you want to use it in a generative language, you would just say disability, and then it's gonna produce the result for you. When we say zero short, meaning you could give a prompt a little longer. For example, you say disability is a, and then it continue on writing. So there's a argument of how you are going to give these shots in this transfer. There's also a concept of few shots, which is providing more context to the language model, like a passage, and then keep asking this question, and the language would kind of, the model would kind of adjust itself by that input that you provide. Quite a complex in a designing model, and I probably explain it quite simple, but basically GPT-2 is really good in zero-shot learning. That's quite known for it. The data set, they use the Reddit platform, and they put all the links of high upvoted articles from web text. So overall, GPT-2 had 40 gigabytes of text that they go through over 8 million of documents. So that was like a biggest, very, the data set significantly improved from GPT-1. And when I'm saying significantly improved, that you can see that what happened in terms of the model and architecture and implementation. Let's look at the layers first. In GPT-1, we get 12 layer. Here you get 48 layers. And there is the dimension vectors of word embedding in terms of, I don't know what is the way to describe this kind of dimensional vector. But imagine that it got 1600 vectors in the kind of conceptual model of word embedding, that it has this ability to represent that number of embedding in one area. And the big thing about GPT-1 is 1.5 billion parameters. And of course, it's 10 times more than GPT-1, because GPT-1 had only 117 million parameters in language, whereas this one is significantly bigger. And of course, it had a larger vocabulary of 15,000 tokens that was very used. So we will see what is the effect of each of these in the next slide, the final slide I have. It comes to GPT-3, which is a great kind of a biggest language model. And I mean, there are some limitation of it that if you pay attention, it's not that everything is great about GPT-3. But the main objective of designing GPT-3 was we want to have the in-context learning. And of course, because of the other two language models didn't have a kind of good capability of few shots, they kind of added this kind of objective to this, that with all the three types of setting, few shots, one shot, and zero shot setting, GPT-3 was designed to respond to that. In terms of the data set, it's probably you have heard this, that how many months it took until they trained these models and the computational expenses that they used. 5 different core providers was used, and the model took really quite long, so they used the entire web. That's why they kind of known as common crawl. And then they of course use web to text, books 1 and books 2, and Wikipedia, the entire Wikipedia at that time in 2020 used to train the model. And what are the model limitations? Surprisingly, GPT-3 is similar to GPT-2, the language, the architect, but there are a few major differences. Of course, the layer has increased significantly. So GPT-1 12, GPT-2 48, and GPT-3 96 layers. And of course, in each layers you get attention heads. So imagine that how much this complexity and computation adds on overall to the architect. And the size of embedding also, in the previous one, GPT-2, we have 1600. Here you get 128. Sorry, 12,000 plus, over, like, has increased from GPT-1. So that's the kind of increase on that, I believe. I'm not sure if the number is correct here. But it's a significantly increase on the word embedding. That's kind of enabling. But having said that, I'm not an expert. I have recently, my research colleague that we work on a research, they have got access to Google AI GPT-3 model, and we got started some experiment on it. I haven't seen the result of the experiment, but the major difference on GPT-3 that people often, it's a language. It's of course the parameters of the parameters has increased significantly, and the layers, but because of the data set has been trained, the number of the data set is very massive that the language model has trained. That's why you see this great result of GPT-3. Having said that, it has its own limitation, and not necessarily it does any kind of reasoning that people think that, like the Guardian article that GPT-3 has produced and make big noise on that. That was one of the significant of it. But again, there has been an experiment that people ask questions and the language is unable to do the reasoning. There are a number of articles and videos and web news on its limitation. So I wouldn't necessarily call GPT-3 as it is a state of the art, but there are limitations with the language. I haven't myself been able to test it yet though. Let's say about the performance comparison of these three languages. So GPT-1 performed better, of course, with the trained supervised state of the arts in all the models, 9 out of the 12 task model. This is a kind of when they designing language model, there are a benchmark that they compare it in the number of tasks. And if you refer to that website, to the Medium article, it's explained what are those tasks. But also, it's also said in the papers, the outcome of the paper. But just to having said that, it's kind of at that year it performed significantly better, and that was like a breakthrough on the transformer architecture. GPT-1 was able to achieve 7 out of 8. So if you statistically compare it, GPT-1 was kind of nearly 70% maybe good, but GPT-2 got 90% good in that one. And it's important to go zero-shot setting. And it's been said that in particular translation tasks, it performed much better in unsupervised model, whereas the outcome of the startup, it couldn't beat the outcome of the other unsupervised model in the other tasks. And of course, there's a concept that is being said and confirmed that GPT-2 does not perform well on text summarization because the way, and most likely you could conclude that with GPT-3 as well, because it has a similar architect. And the reason is probably, I don't know the actual reason behind it, to be honest, in terms of the architect, but it's been said that it doesn't do well in text summarization. With GPT-3, we got the language model. It performed better than language models such as this. These are the two famous language models that it performed much better than them in zero-shot setting. And then, however, it could not beat the state of the art. But it improved the zero-shot state of the art. So GPT-3 is really good in, if you put a prompt to it, it will immediately respond you with some interesting results. So it performed better, but it didn't beat the actual state of the art for other tasks. And it does reasonably well in NLP tasks. In closed book question answering, or when we say it does really good on translation or something like closed book question answering, you probably have seen it, how GPT-3 is really strong on kind of coding. If you people have done videos that how GPT-3 pick up on coding. Like you type something in the code and it writes it in Python for you. It's because of course, the number of data set has been provided, the model trained significantly well on it, but it performed reasonably well in other things. But the more people experiment with GPT-3, its limitation appeared. And also one thing that I want to say on side, one of the main problem of all these three languages today was the kind of we empower the language model, but the problem of bias has been appeared in language models, and it's concerning people with work with language model. And because this language model are being used in search engine, in device, built in all the query things. So it's important to be aware of the because our text in general, we generate text with bias every day, and these language models are trained on the same text that being generated. So we must be really careful of the bias appeared in language model, and my own research is on that. We are looking into bias in casual language model, and the reason is to making awareness of this, not that to saying that the language model are not good. It's just making awareness that be careful of when you are training on a text that has bias, what you get is also again bias. So that's an important thing to consider. Having said that, I'm kind of towards the end of my talk today. I have good news for you. This has been a very complex topic, and I don't know how much you get out of it, but it's not really difficult to work with language model in a way. So don't think that you need a PhD to kind of go and try this out. I've put a simple code here, which is also you could go and try. The Medium article has a link to a very complex GitHub repository, and there are a lot of examples. One of the really good libraries that use language model are Transformers, our Hugging Face library. So if you install the Transformer library that has been implemented through Hugging Face, you could easily call this module, and there's also a pipeline that there's a package for it that you can call it. And you could call GPT-3 smart size, medium, extra large. There are different sizes for it. And by calling the tokenizer and by initiating the model, and let's say that you got a prompt of disability, and the main thing that you need to do is to call the to tokenize the code, the prompt, what the sentence that you have. And here I am calling the sentiment analysis. I wanted just example. This example is looking at it at the sentence that being returned by this word, and then we're looking into kind of sentiment analysis of that. So we call the classifier, and of course my length is like 50 tokens. You could make it longer or shorter, and we are looking into top 95%. And then what this classifier returns, it returns a kind of, you tokenizing it again, it's a kind of, it returns a sample output, and then of course we tokenize this, and then we give us a decode output. And once you check the decode output through the classifier, you get the result, you get the score that, for example, what is the sentimental analysis of that. Or at this point, even if you don't want to call the classifier, the input IDs and the decoder tokenizer would give you the sentence that been generated by language model. So go and try this out to just see how a language model giving to you, and I hope this was a good overview of this complex topic. And feel free to reach out to me as well. I guess that brings me to the end of my presentation, and happy to have any questions.
So so if anyone has any additional questions, please put them to Q&A, but we do have one question. In training GPT-3, did they also put in the data that GPT-2 used, e.g. the Reddit data?
Very good questions. I don't think so, no. I think they GPT-3, of course, GPT-3, for example, use all Wikipedia, whereas GPT-2 used the data set was different. But because GPT-3 look into entire web, they crawl the web text, there might be some possibility on GPT-3 data has been used. But if you read the GPT-3 paper, they actually, the authors describe a complication when they did the training, they realized that some of the data, I can't remember exactly what part of the data was, but some of the data has been feeding that they shouldn't. They kind of said it in the model, in the paper themselves, but then because of the expenses on the computational of training this model, they didn't stop the experiment. And this has become a concern for a lot of researchers that use GPT-3. They kind of saying that the model didn't train properly. But having said that, I don't think they use GPT-2 data set. No, I think that's the answer. Yeah, Emma, thank you very much for putting those webinars on. You put that, yeah. Cool. I think.
So just two more questions come in.
Yeah, sure.
So first question, what model is currently the best for text summarization?
I think with the training, the text summarization, we actually have very good conversation with our colleague in Microsoft today, and one of our program managers, they were presenting a really interesting conversation. I think text summarization, because of we are talking of expressive and abstractive, so two different things. There are a lot of expressive one that they're looking into the training using a trained language model, kind of, let's say I would example of BERT. So we use a pre-trained language model, and we embedded with the new text, and it kind of identified the most similar words, sentence or passage to the inquiry, to the query that you have, or the summary that you want to have, and it kind of summarized that for you. It doesn't generate anything. In terms of generative, like kind of abstractive one, that kind of generation, there are some works that actually a team in Edinburgh, a PhD group in Edinburgh research group has been done it, and they're looking into interesting approach of combining BERT with other language model. I can't remember exactly, but I'm happy to give you the detail of it. They seem to improve the abstractive one, the generative one. But in general, generative language model, something like GPT family are not recommended for summarization. So for summarization, we need, if you are looking for expressive, a lot of pre-trained language model are working very well in that scenario. For the abstractive, I think the field is still growing. There are a lot of experimental results that the different architect of transformers are being applied by different hidden layers and things, trying to get the kind of abstractive summarization. That's the most difficult one, and the field is still growing. I could refer you to the paper of those Edinburgh team. I looked at them a while ago, but I don't have them in my mind. But feel free to reach out to me. I can provide you with that link.
Thank you. And the second question was, what is the best model for generating questions from text?
A very good question. I think GPT-2 right now is a really good for generating questions from text. I think, again, it's, if you want to say, you have a text and you want, is it like you still want to get the question summary from that text, or in general you want to generate a questions? This is something that still people are working on it. Language model seems to be the right way to do it, but there are examples of GPT-3 that it does good on some of the generative text, sometimes it doesn't. So in general, if you tell you one principle, the more you do the word embedding, the more advanced you done on that, and the architect get attention layer to it, the better generative text you'll get. And it seems that GPT-2, my own experience of GPT-2 that we are running for this experiment on bias, it's really interesting that we get really interesting response from the language. So I would say still GPT-2 is a good one to go, but not on summarization, just a generative. But then again, you need to make sure that you do a good word embedding on top of that. Hope that answered the question.
Thank you. And that's the last question.
Very good.
So just like to say thank you, Lida,
Yes.
for this talk, and thank you everyone for turning up.
Thank you.
And
thank you, everybody.
Thank you. And Emma, if you any final comments?
No, I don't think I do. Just to say thank you, Robin, for organising this series. Lida, thank you so much for today, and also thank you to everyone who's attended throughout this series. I did post a link into the Q&A of where you can watch all of the on-demand content, so it is still there to watch. But yeah, I hope we can do another series like this again soon. And thanks once again, everyone. Yeah,
thank you, Emma, and I also want to thank you and Robin. I think I just got last question, if that's all right. I just answered that. It says, is GPT language useful to generate text for a specific industry? I think there's a kind of conversation a lot about this at the moment, and I'm not an expert to kind of say this is right. But my understanding as an NLP person who understands the architect and thing, the concept of domain specific in language model is no longer a big concern in a way, because the whole idea of language model is to be domain independent. So when a language model is being trained in whole Wikipedia, it's saying that it's not concerned anymore with the specification or domain applicant, because it's going to be, we have a lot of concern with ARNN, with LSTM, with lot of other language models, bigrams and n-grams language model with the domain specific, because the order of the words and the content are matter. But when a language model such as GPT-3 is being trained and it's really on the attention is in context, the domain is no longer a challenge here, and that language model can be used in any model. And a good example for it, again, this is something that I logic myself and I understand, but I'm sure there are a lot of conversation. But when you do on search engine, when you search inquiry on your current search engine on Bing that is on MS Turing language model, we're not specifically giving any context. We just ask a question on a medical question. The response you get is actually medical context. Whereas the same search engine, you ask a question on industry and in manufacturing, it gives you the return answer by manufacturing context. So I think the whole idea of this current state of the art language model to be domain free, domain independent. I hope it helps. Thank you. And I guess that would be the final answer. Then you can finish the talk, Emma. Thank you for that.
Thank you.
Great, thank you so much, Lida. And yeah, with that, we'll wrap up and finish off today's session. So thanks once again, everyone.
Thank you, everybody. Cheers. Bye.